Welcome back to the clustering module. So far, we've learned what is k-means and we've also implemented it from scratch. So I hope you have a clear understanding of how k-mean works at this point. But there are certain situations where this algorithm fails to perform well, or at least up to our expectations. Let's look at these challenges which we can face when we're working with k-means. We'll also look at the solutions for these challenges. So one of the most common challenges which we face is when the size of clusters is different. Let's say we have points like this. If you look here, the left and the right clusters, this one and this one are of small size, whereas the central cluster has a much bigger size. Now, if you apply k-means on these points, the results will be something like this. If you look, we have 3 clusters here, and the shape of these clusters is almost the same. In the original figure on the left, the shape of the clusters is different, whereas when we applied k-means on these points, we got these shapes. This is the challenge with k-means. It always tries to make clusters of the same shape. Another challenge is when the density of points is different. Let me explain what that is. Let's say we have these points. Now, in the red cluster here, it's much more spread out, whereas the points in the remaining 2 clusters are very closely packed together. If we apply k-means on these points, we'll get clusters like these. The compact points have been assigned to a single cluster, whereas the points that are spread loosely but were in the same cluster have been assigned to different clusters. Again, k-means is facing difficulties when dealing with points of different densities. In k-means, we randomly initialize the centroids, if you remember, and this can also create problems. Every time we might get different clusters. In such cases, we can train the algorithm multiple times and then choose the clusters which give the least inertia or optimize other evaluation metrics like the done index. Now, regarding the other 2 challenges that we saw earlier of the different size and densities, what do you think is the solution? One solution is to use more number of clusters. We used 3 clusters earlier in the examples and saw that the results were not appropriate. Let's see how the results will be when we increase the number of clusters to, let's say, 10. So here, I've used 10 clusters and you can see that the clusters are now making much more sense. So when the size of clusters is different, we can always lean on using more clusters. Similarly, using 10 clusters in this example also gives us much more meaningful clusters. Here, as you can see on the right, we have 10 clusters, but let's say the final requirement is only of 3 clusters. In such cases, we can merge the closest clusters until we get the required number of clusters. This is how we can overcome some of the most common challenges that we face when we are applying the k-means algorithm. Now the next question, and I'm sure this has crossed your mind, what should be the optimum number of clusters to have? Should we use 3 clusters? Should we go for 10? Is there any way to get the optimum number of clusters? That is the $1 million question. So in the next video, we'll look at the methods that can help us to decide the number of clusters. It's a very interesting video and I'll see you there. Thank you.